Welcome to our webinar, Vibro-acoustic analysis for noise reduction of electrical machines. Then vibrations and noise have three sources, aerodynamic, mechanical, and electrodynamic. In Flux and with the new feature, we will focus only in the electromagnetic source of noise and vibration. We know that when we excite a machine, there is a production of a good forces which is torque, and parasitic forces which induce vibration and noise later. Then actually we have a need to couple two domains, electromagnetic domains, which is Flux, and mechanic domains, which make vibratory analysis and acoustic analysis. We have instead proposed to make a coupling between these two domains to make a vibroacoustic analysis. Then in Flux we will calculate magnetic forces, and in mechanic softwares we will make vibroacoustic analysis. And this vibroacoustic coupling allows a simple and quick magnetic forces export to mechanical software. The vibroacoustic coupling in Flux is available in 2D, 3D, and Skew, and it allows exporting forces to two mechanical software, MCS NASTRAN and LMS Virtual Lab. This vibroacoustic coupling is available only for transient applications. Then in this new feature we have two methods. And direct method, it is to couple Flux to NASTRAN, and the direct method to couple Flux to Virtual Lab. Why indirect method? Because we have to import mechanical mesh from NASTRAN in Flux. In Flux, we will calculate magnetic forces and project it in the mechanical support. And when we do this, we can export finally the magnetic forces on the mechanical support to NASTRAN. Direct method to Virtual Lab. Here we calculate directly the magnetic forces on the electromagnetic mesh, and we export these forces to Virtual Lab in a file .env. Okay, in Flux, new functionality apply new dedicated context. We can access for those who have Flux. We can access to this new context via menu computation and open mechanical analysis context. In this new context, the main functions available are creation of the new computation support, computation of the magnetic forces. We can visualize magnetic forces, and later we can export these magnetic forces to NASTRAN or to Virtual Lab. NASTRAN with file extension .bulk, and to LMS Virtual Lab with file extension .env. The principle of this method is first we build a geometry in Flux. This same geometry must be built in LMS Virtual Lab. In Flux, after building the geometry, we will make it and make physics parameter like material, mechanical sets, etc. We will solve this problem, and in this post-processing, we will calculate the magnetic forces and visualize it. If it's okay, we can export directly the magnetic forces calculated in Flux to LMS Virtual Lab. In LMS Virtual Lab, we will import this env file, and we will make vibroacoustic analysis in LMS Virtual Lab. In Flux, we will first calculate the magnetic pressures with a method already used in Flux, which is the FMAC-S. The computation must be done on the borders between magnetic regions and higher or vacuum regions, like stator T, for example. The magnetic pressures are transformed to magnetic forces on each node. This method is a general method which can be used for all electromagnetic devices. Here, a small schema to illustrate what I said. In the electromagnetic mesh, we will calculate magnetic pressures on each node of the magnetic mesh. And from this magnetic pressure, we will deduce the magnetic forces. The implementation is, as I said, in Flux, we have to build the geometry, and after this, we will make the mesh and physical parameter, and we will compute the magnetic forces. These magnetic forces, we will export it as a UNV file. And in LMS Virtual Lab, after preparing the 3D geometry, we will import this UNV file. And finally, we make a vibro-acoustic analysis. Then the first step, we will go on the mechanical analysis context. In this mechanical analysis context, we will create our force support. Here, for example, we will choose the boundaries of the stator T. This computation support is created for the whole machine, and the support will be exported as a 3D support when we export these magnetic forces to LMS Virtual Lab. We will launch the calculation. The computation must be launched on one mechanical period. In Flux, you can choose to make the computation on one or a quarter of mechanical period. For example, in this case, one mechanical quarter of mechanical period is this one. In this new context, we can choose to calculate only the magnetic forces or to calculate the harmonics of these forces also. And later we can visualize each harmonic or all the magnetic forces. After creating the computation support, we will create a force computation. We will choose which method to use, if direct method or indirect method. We choose the time interval which corresponds to the quarter of the mechanical period, and we choose to if we calculate forces and their harmony. And we can make OK, and the calculation will be done. After this, we can visualize these forces. Here, for example, we can visualize the harmonic force of the magnetic forces. I will show you this in Flux directly. And after this, the last step in Flux is export the magnetic forces as UNV file to LMS Virtual Lab. For the direct method, only the time signal is exported on each node of the Flux mesh. Then we can choose to export for NASTRAN or for Virtual Lab. Here, in instance, we calculate for the direct method. If we are in 2D, we have to indicate the number of layers on the depth of the machine. In the LMS Virtual Lab part, we have to import the .unv file in LMS Virtual Lab. The UNV file containing the electromagnetic surface mesh and the time domain forces is imported in LMS Virtual Lab Acoustics. The user can inspect the force distribution per time step and animate the forces in time domain. The next step is the structural model plus the model basis. This model contains stator, winding, end caps, and housing. We are in LMS Virtual Lab. One homogenized but orthotropic material is chosen to model the stator. In first instance, a model basis is used to capture the dynamic of the structure. The second step is forces mapping to structural model plus model basis. LMS Virtual Lab maps the electromagnetic forces conservatively from the electromagnetic surface to the coaxial structural mesh surface. After this, a Fourier transform provides frequency domain forces. These forces are used to compute the vibration response, and finally, we make an acoustic response in LMS Virtual Lab. This is about the first coupling method, which is the direct method to LMS Virtual Lab. The same thing I will talk about the principle and the implementation. Create geometry in Flux. The same geometry must be created in MCS NASTRAN. In Flux 2D, we will follow the steps until post-processing, mesh, physics, solving. In NASTRAN, we will create a mechanical mesh which contain mechanical nodes. This mechanical mesh support will be imported in Flux. In Flux, we will calculate magnetic forces and project it on this mechanical mesh to obtain the forces on the mechanical mesh. This result will be imported in MCS NASTRAN. And finally, we make a vibratory response and acoustic response. And in fact, the vibroacoustic analysis is made in the two mechanical software, LMS Virtual Lab or MCS NASTRAN. It is an indirect method because first we import mechanical mesh. After that, we export the mechanical mesh with magnetic forces. In this method, actual tensor is used to compute magnetic pressures. This method available only for the rotating machine, not like the first method. The first method is a generic method. It is available for a rotating machine and for all other electromagnetic devices. In this method, magnetic pressure computation is done in the air gap. The computation support can be a circle if we are in 2D, or a cylinder if we are in 3D or Skew. Then the vibroacoustic analysis must be done on one mechanical period, like for the direct method to LMS Virtual Lab. The time steps must be small enough to take into account the space harmonics, to take into account time harmonics. It is possible to consider only a quarter of mechanical period, like for the direct method. Two magnetic pressures component will be calculated in the arcade, tangential and normal. The normal component is calculated with this expression, and the tangential component is calculated with this expression. As I said, we have to create a mechanical support in MCS NASTRAN, export it to Flux. This mesh generation is done inside NASTRAN. We have to select the faces to be considered, generate the point bulk file containing the mechanical mesh information. The mechanical mesh is defined in 3D. Next, in Flux, we will import this mechanical mesh as a point bulk. This is the technical information. In Flux, we have to use the two coordinates to control the position of this mechanical mesh. The units are taken into account, and this mechanical mesh is done in 3D and we can visualize it in 3D even if we are in Flux 2D. Then the principle to calculate electromagnetic forces and to project it in the mechanical mesh. Then in the air gap, we will create a computation support. We will calculate a magnetic pressure, and this magnetic pressure, we will add it to have one magnetic pressure. From this magnetic pressure, we deduce the total force on the stator teeth, and this total force we will divide it on the node on the depth of the machine. This is in 2D in fact, and when we are in 3D and Skew environment, we use the method of ghost point. And the same thing in the air gap, we will create the computation support, and we will project this point, ghost point on the computation support. And from this, we will calculate magnetic forces which be divided on the different mechanical nodes. The time signal of the magnetic forces is associated to each node of the mechanical mesh. In each node, an harmonic analysis is done. The harmonic one corresponds to one mechanical round in each mechanical node, and for each harmonic, the amplitude and the phase are calculated. The amplitude and the phase are calculated for the two components tangential and normal of the magnetic forces. Here, the same thing. We will prepare the geometry in MCS NASTRAN. We will make the same thing in Flux. For MCS NASTRAN, we will build a mechanical mesh containing a mechanical node and export it as a point bulk file, which be used in Flux. In Flux, we will prepare our project, geometry, mesh, physics, and solve this project. And finally, in post-processing, we will import the mechanical mesh and calculate the magnetic forces, project this magnetic forces on the mechanical mesh, and finally export these magnetic forces to NASTRAN. And in NASTRAN, we will import this file containing magnetic forces to make a vibro-acoustic analysis. Okay, and in NASTRAN, we will prepare the geometry and create a mechanical mesh. In Flux, we have prepared our geometry and solved it. And in post-processing, we will go to the mechanical analysis context. In this mechanical analysis context, we will import the mechanical mesh. Here, the mechanical mesh is this file, mechanical support interface bulk. We will import this mechanical mesh, and we can visualize it in 3D, even if we are in Flux 3D. Then we will launch the calculation. Before this, we have to create a computation support in the air gap, and this computation support must be on the carter inside the air gap. Inside the stator, if the computation concerns the stator, and in the carter of the air gap inside the rotor, if the computation concerns the rotor. And here also in this indirect method, the computation must be launched on one mechanical period. As I said, in Flux you can choose the carter of this mechanical period. And in this new context, you can choose to calculate only the magnetic forces or to calculate the harmonics of these forces. After creating computation support, we can launch the computation of the magnetic forces. We have to indicate the radius of this computation support in the R gap and the slot opening. We have to choose the time interval here, which corresponds to the capture of the mechanical period, and choose if we will calculate forces. After this, when the calculation are finished, we can visualize these magnetic forces on the mechanical mesh. Here also I can show, for example, the harmonic for on the mechanical mesh. If all it's okay, we can export the computed magnetic forces to NASTRAN as a point build file. We go to force computation and export forces for NASTRAN. In NASTRAN also, we will import this file containing mechanical mesh and magnetic forces and make the vibro-acoustic analysis. I will just open a Flux to show you this. Then here I have created the computation support. Computation support to make a calculation to LMS Virtual Lab. Computation support to make a calculation and export the calculation to MCS NASTRAN. Here we can visualize the computation support in Flux 2D, and the computation mechanical mesh support is in 3D. I have calculated the forces on the support that I create to export to LMS Virtual Lab or to export to MCS NASTRAN. Now the calculations are finished. I can show the harmonics, for example. I will show the harmonics 4. And if I'll change the phase of this harmonic, you can see that this harmonic is rotating harmonic. If I show the harmonic 1, for example, this one is for LMS Virtual Lab. This one is for NASTRAN. This harmonic is a pulsating harmonic. Okay. In conclusion, we can say that the vibroacoustic analysis for noise reduction of electrical machines, we have an efficient process using expert tools. This new coupling method is a proving methodology offering convincing results in a reasonable computation time. Embedded dedicated tools in Flux, available in Flux 2D, 3D, and Skew, including fast and easy geometry creation in Flux and the mesh, thanks to motor overlays, for example. And this new feature in Flux allows us to make a connection to LMS Virtual Lab and MCS NASTRAN, etc. offer a strong support and efficient consulting services. Thank you for your attention.